Okay, so welcome to today's HKAE TechTalk. We are very fortunate to have Professor TAO Xiaoming here to deliver a talk titled Fiber-Based Tactile Emulation Mechanism and Intelligent Wearables. So let me briefly introduce Professor TAO Xiaoming. And Professor TAO is founding director of the Research Institute for Intelligent Wearable Systems and the chair professor of Textile Technology at the Hong Kong Polytechnic University. She is a fellow of Hong Kong Academy of Engineering, the Textile Institute, the International Society for Advanced Materials, Asia Pacific Artificial Intelligence Association, and the American Society of Mechanical Engineers. Focus on smart fibrous materials, devices, and intelligent wearable systems. She has published over 400 papers in top journals like Nature and Advanced Materials, and she has also invented a lot of new technologies. Some 20 inventions have been applied in industry worldwide, including 9 startup companies. Okay, so now let's welcome Professor TAO.
Good afternoon, Professor Xu and fellow students. I guess you are students and maybe some colleagues. I'm Xiaoming Tao, and I'm so glad to come here to Hong Kong U again to share some of our thoughts in the research for fiber-based smart materials and structures. Today I will focus on tactile emulation mechanism and intelligent wearables, because that's our current research and funded by RGC under theme-based research. Some latest progress probably like to share with colleagues. Now, my talk have several parts, and first I give some introduction on the background and the rationale of why and we do the work. What is the hypothesis for this study? Then I will probably describe 4 elements in this research. First, how can you put all these functions, including microelectronic functions, into textiles? Probably here, audience may not that familiar with what is textiles. Most familiar one is the one you wear on your body. And you do realize at this moment, most of them do not have electronic functions. Okay, then how to impart these functions into textiles? That's just one of our research. And the second part is in these textiles, we want to have important function called sensing. And fiber-based, that means it's thinner than your hair. Put them into this kind of structure and can sense a lot of mechanical and environmental conditions. That probably is my second issue. And then after you sense something, you detect some signals, you want to do something. That's actuation. That's our recent work on magnetic fiber and structures. That actually is actuator. And then we also working on a large scale actuation. That is use a numerical method, use a fluid incorporated in the fabrics, then to drive the kind of textiles to achieve certain functions. And so these will be the 4 parts today I'm going to share with colleagues. Okay, let me start with our motivation. Why and what fiber-based wearable multisensory emulation? Now, first, what is this emulation? It's a use of advanced technology to simulate or replicate the experience of human senses. We all know humans have 5 senses: vision, audio, and smell, and touch, and the taste. At this moment, probably most researched are the visual and audio part, and the technology associated with them are relatively quite mature. That's based on image, on video, and sound. Okay, and less studied, put all them together. They're tactile. That's a touch, sense of smell, sense of taste, tasted by your tongue. So then why we choose fiber-based platform to do these things is a fiber-based one form kind of a flexible material where people are used to them for 1,000 years. So they will have least resistance to use them, feel convenient. Okay, so for this reason, we proposed a study that is started last year. Okay, now it's almost 1 and 4 months now. So this is the progress we probably today share with colleagues. Now, before that, probably let me to say something about a human sensory system. Actually, this is a neural network, not an artificial one, it's a real one, sensing network responsible for the conscious perception of touch, pressure, pain, temperature, position, movement, and vibration. So in this system, actually have 3 components. Most time people talk about tactile, focused on the surface touch, where under our skin, not very far away from the surface, we have a different kind of sensors that can sense this. And the second group is deep down that sense the joint position and the fascia. That's a kind of elastic structure link the bones, okay, and the muscle stretch. These are deep down ones, are much less studied, but in sports, in aging, in rehabilitation, this part actually is often ignored component for study. The last one is perception related to pain and temperature. Tell people you are in danger. This normally, the third one and the first one are joined together in most study we see in the literature. But for us, we would like to put them together because the end use of this kind of emulation is to emulate human sensory. And then you wanted to do something. Most doing something is related to sports, related to health. Therefore, the second part is you cannot ignore them. Okay. Now, the question and challenges we are facing. So I explained this system, and then little is known on the mechanism of programmable fabric actuator. That means a fabric that can do something according to your will, can be written in a program format, so controlled by digital means remotely. The person cannot stay with us, probably it's far away, thousands of miles away. So there's very little known, okay, when we proposed. Existing tunable fabrics do not have a sufficient feedback, allow this program to go on. And there's no models, no algorithm for such a fabric actuator. So entire area, the sub-area is empty, was empty, okay, before us. The question we ask us is whether and how the fabric actuator meets the requirement of tactile emulation. The answer, of course, is no. Okay, but then ask ourselves how we can do that. What type of fabric structure and operation mechanism can deliver such a rendering behavior? And we want to control interfacial forces. Interfacial forces meaning pressure, friction, shear force, and so on, rolling, etching, so on. And shape, texture, and temperature. And if we can do that, how can we control them in a kind of mature and reliable way? So these are the questions we ask ourselves. And approaches we used, actually, we divide the task into several subparts. First one is to look at the sensing. First, you want to duplicate something, you must know exactly the original one, how they behave. So the sensing is important. Accurate, reliable sensing network using fabric structure, and also using some machine learning method to get a higher level of accuracy. It's the first task. This part is, relatively speaking, it's been long researched, so there are some established technologies we can adapt very straightforward after some modification. The second part is really, the missing part is fabric actuation. At this moment, very seldom we see people have a digitally programmable fabric that can do a lot of things at this moment we cannot do. So one thing is we want to do a tactile one. We want to have a different level of actuation. Because on the surface, we all have such an experience. If you, in a windy day, your skin, you can feel the breeze cross your skin. That's a very minute force. And then when you go to massage or something, you feel very big force on your skin. You sometimes feel pain. When you have an accident, you break your bones, right? So this level will require different level of actuation. It's the same in the sensing, okay? And actuation, we divide the task because before there's no. So we started with millimeter level actuation. That means the displacement is in the range of millimeter. And then we go on for cm, 10 or a little bit of several cm level actuation. That are probably similar to massage. That's where the rehabilitation people or massagers, they will use. Okay, so these are the two parts. And all these things need to work together with control. Control, we need to have an algorithm and models. So this is a piece of research we're doing at this moment. Now, to build such a system and to study all the problem and answer those questions, we probably need to see what we have done in the past and what we can use them. And so first one I would like to share with colleagues is electronic textiles. That means the textile can do the electronics function. What are the electronic functions is we do generating, transmitting, moderating, detecting electrons. That's called electronics, right? And so whether a fabrics can do the similar thing, so right now we can do that. The way we do it, because we want to have a very accurate and reliable electronic functions, not just for the sake of writing a paper, publisher have this behavior. They should work similar to your computer or mobile phone, reliable, okay? So what we do is we put microelectronics chips into a textile structure, a threads in the fabric. When you look at your fabric, you can take one threads out. That's many fibers together. Fibers, individual elements, basic elements, they twist together. Okay, so we put it this way. Here, I cannot leave these points, right? And you can see on the bottom line, the blue square, that's just microelectronic chips. At this moment, the very small, and the thickness can be 20 micron, probably for a quarter of hair thickness. So hardly you can see it. So you can if you can put these kind of chips into one-dimensional shape, into a threads, and this is how we did it, and put them into this structure. It's called yarn. It's assembly, one-dimensional assembly of many fibers. Okay, and you put these. You need a electronic function and also mechanical integrity. You don't want it to break, right? You need to protect the chips, and also easy to go through the manufacturing, and easy goes through to washing to wear. Now, we have two types of, to make this happen, we need a substrate where the microelectronic chips can sit on, where they can be connected by design, right? And so we use two types of substrate. One is a paper. Paper, remember, paper is fiber structure. A lot of short fiber bound together. Okay, so we make electronic circuitry board, and assembly is putting chips on, and using this aramid paper as a substrate. The left, on your left side, that roots. As comparison, we compare that with a polyimide, PI substrate, and using a subtractive roots. The other one is additive roots. Okay, so we study them and put them into this one-dimensional circuitry. And here is some results. We have 3 samples here, double-sided one-dimensional fabric circuit board, FCB. And then we look at the thickness. Sorry, apologize, that's a micron instead of mm. We have different thickness. The thinner one is 100 micron, a little bit thicker than your hair, okay. And then we have bending rigidity, that's very low, 0.15, and as compared with other. And the double-sided circuit board can put 4 legs or even more leg of the chips into the structure. If you have only LED like Christmas tree, 2 legs single-sided is okay. But if you want to have a full color, you need 4 legs and or even more. So we need to use this double-sided one. To make this substrate, we're using number of different fiber structure. The B one there, you can see is how this paper looks like, start with cross-section. And then we put some metal coating on them. They become a little bit regulated. And then we put a protective polymer, encapsulate them. We have 3 types of them. Most probably noticeable one is, you see we did the rubbing test. This is standard test. Okay, you have a piece of abradant, and at a certain pressure, you move the abradant against the circuitry. This is a diagram, that's as A here. You can see the longest enduring time is 50,000 cycle without break. The loss is small than 5%. Why? Without any treatment or even with a metal coating, and their life endurance is very low. Okay, so this one, 50,000, is probably can be used in many applications now. And this is the surface of this. Now, for wearables, probably everybody knows your clothes need to be washed. So washability is very important. And we put this standard test. It's a 1 meter long, water long column. You put your circuitry at the bottom of that over a certain period of time, and passing and not passing. So what we do is we put a colorless dye on the piece of circuitry. If water seeping through the structure and the color change, you can see those one in red circle. These 3 actually have water seeping through. The other side is encapsulation is successful, so there's no color change. Okay, then personate, or those waterproofed one, or water steel leakage one, the other one we're using different technique to identify which one would be better. There's 100% against 70%. So this problem is solved. Then the next one is there are many more tests need to be done. Some in boiling water, in icy water, in artificial sweats, and in seawater, and bending, and so on. So these substrate actually pass through, and very, very nicely. Because of the technology, now we can put in all sort of microelectronics chips into a textile structure. Here I'm demonstrating 3. First one, you can see, this is a 4-color fabric. It's like a tower with a different color, full color display. Not display, this is just lighting, right? And potential, you can put it into display. Into display is like this.
Funny how this all looks different,
Have a sound,
but it feels
can
the
talk
same.
to it,
Like
and
how life
can
never stops
display
changing, something
animation
never
you made
changes.
on your computer or on the mobile phone. You upload it to the fabric, and then can display. And then that yellow one is a touch board. You can control which display you want and this. Okay. So this is a video and audio interaction. And you can imagine all the so-called microelectronics things can be installed in your fabric. Okay, and can do a lot of weird things. Now, this is the next one.
Hello, 小朵，
This is talk
打开
board,
设备。
chatbot. Okay, Claudia. It can switch on, can talk to people, and we are working on a soft program, so they can talk to old people, talk to children. Okay, conversation. Okay, so this technology is ready after several
Hello.
years research. Now we move on to look at the sensing part. How to, when you have a touch sensation, how can you measure it precisely? And there are many techniques can do to a certain degree, but we think the most accurate one probably is fiber optics, but the most expensive and not suitable for wearable. I probably will say something about this, but doesn't say in principle it. How can I? Yeah. Now this is done quite more than 15 years ago. Glass fiber can, optical fiber can used as a kind of moderating sensor. It's in the core of the fiber. You have a periodic structure. They act like a selective mirror to select certain wavelengths to let it transmit or let it reflect, selective. That's important. And when you stretch the fiber have a very minute extension in the actual direction, then these wavelengths actually shift. So it's a very accurate measurement. However, this kind of fiber is used for communication, telecommunication quite a lot for many functions. But can that be used for our fabric? No, answer is no. Because glass fiber is dangerous. It breaks and gets into your eye. You need to wear goggles to protect your eye. So for that reason, we use polymer to make similar structure. Okay, we use, I do not go to the detail. We need to make, the requirement is make some fiber have two structure. One is a core, around the core, and outside is surrounded by another polymer. These two polymers must have a difference in its reflective index. You can see this picture on the right side. And this is a measurement. You can see in the middle, there's a 16 micron in diameter. That's the core size. And outside is 239 micron. That's just the fiber we measured. Okay, and then reflective index measured. Okay, the difference is minute, but that's sufficient for this sensor to be made. Okay, but how can make this fiber? It's a little bit complicated. In the core, you need to put a photosensitive material that has a transition under UV light and cis and trans conversion. This conversion can cause the reflective index change. Okay, very minute change. And so we use that as a core and once this fiber is made, we put them into the laser system. The laser shine in this box. I'm sorry, I can't use this one here and here. Can you see the cursor move? This is a fiber with a core, and the laser is shines through a mask. So we call masked exposure of UV light, intensive UV light pulse laser. So by doing that, you cause this transition. You make a permanent moderation of the reflective index in the core of the fiber. Now, that is enough. Once this fiber is made, what do we do is we put them, these are two fiber in blue color. You can see those little line there. That is a periodic structure, cause the wavelength, selective the wavelengths. That's the core of the measurement. Okay, and these two fiber, why we need two fiber? One is measuring, when you compress it, the orange color, that's the elastomer. It's like a rubber. It will stretch. Okay, when you stretch this fiber. So that fiber is an extension in this direction that measure the pressure. The other one is on shear. That one has a tilt, TFBG. Okay, that's a tilt fiber back grating. Sorry, this is a jargon in the trade. Okay, so we have two fiber together. You can see. Then you can simultaneously measure the pressure and the shear force or friction on the surface, and this mathematical expression says the sensitivity is really high. Actually, in fact, they are the highest reported. Okay, and there are many electronic means you can do, but the optical one is a lot of sensitive than the electronics one. Okay, why we don't use them? It's not because the fiber not ready, not good. They are very good already, but the problem is the detecting device is too heavy, too bulky, too expensive. You need an optical spectrometer to measure it. I remember we bought one, it's $200,000. So you cannot put it into wearable system where people can't afford it. Only for big buildings and or trends, these kind of things. So the technology is limited by the detecting circuitry. And I always ask our electronic engineer to think about how to make a very small, cheaper detecting device called integrator. And fortunately, nowadays, people realize and start to do research in this area. Okay, so these also have a problem with coupled temperature. It's affected by temperature. People said, what about humidity? Humidity is less sensitive, but the temperature is affected. So need a compensation on temperature. Therefore, the structure, you can think about it when you put the fibers into different direction in the piece of fabric. And then you make a sensor, large area. You can put each moderating area can be 1 point. So we can put a very large area, like on these carpets, or even in runway, in airport or highway, can be 1,000 or 1,000 kilometers long, because these fiber can be made that long. Okay, and so this is a nice technology we can use in laboratory. We can demonstrate, but in real application, sorry, at this moment the technology is limiting its use because the cost is high. Okay, but that doesn't prevent us to think whether we can find an alternative way to achieve a similar level of accuracy and reliability using other means. So the work is still going on. There are quite a few promising routes we are still investigating. So probably in the future, I can share with you some nice results. Okay, we have this integration. We can put all the chips together. We can have a sensor to sense how the external force or the movement on the surface. Now, the question is, if I want to do something, I want to grab it, or want to give it a touch to it, you, as a user, probably you wear a glove, you give yourself a slight touch. And I'm wearing another piece of device. I can feel how much your touch is. Or you can touch a piece of paper. You feel this paper is sticky or smooth. And how can you translate to me? You say sticky, smooth. How much? Don't know, right? At this moment, no way you can translate that. So with this kind of emulating device, you can, 1,000 miles, you feel that I measure it, and I sense that and transmit the data to my side, and I duplicate that sense by using my device. Okay, that is our total goal of this emulation. Okay, so we need to do something now. Do something, early on I said we need a different level. First level is a millimeter. Millimeter meaning maybe 10 hair together, putting together, a little bit in the order of 10. Okay, so this, how can we do it? So this is our recent work. We make a fiber. The fiber is 20 micron, 1/4 of hair. Okay, and this hair, this fiber contain hard or soft magnetic particle in there. Okay, and in this particular case, it's a soft one. What does it mean? That means residual magnetic strength is low. And that means you put an external field there, it immediately do something. When you move it, it disappears. The residue is very small. So you can do a program, apply external force and disappear. And then you can achieve a lot of action. What we discovered from normal people already know is if we have rods and in a magnetic field, it will rotate or bend, right? If hold at one end. But they do not know if we put many such rods together, you twist them together, and these rods actually the strength, the stiffness increased by several dozen times, become hardened. So we call stiffening. There are two effects. This is something unique of the fiber assembly. This you put together. In other words, you can think about you have a rope. Initially it was soft and pliable. You can put it there. When you put a field on them, certainly become hard, real rods. It's not pliable. If we put such a close on, right now my pants is very easily changed. I go with it, right? If I fell down, I break my bones. I don't have any means to support myself. My pants become a Band-Aid, and that stiffen your leg. Can temporarily help you to fix your wound, okay, to prevent further injury, right? This actually is some dream from Army. they think this is a good one. Okay, other applications can be think about this. So during this process, we found a single yarn with a fiber twist together have this behavior. Then we make this fiber several, in this particular case, 4 kilometers long, very long fiber in a kind of a pilot study. And it's not mass produced, but it's already significant amount. And those particles are dispersed inside the polymer matrix in certain way. And then these fiber made, we put them into a kind of fabric, two types of fabric. The first one, on the top one, is very similar to your clothes. It's a two group of yarn. One is from this direction, the other one 90-degree, crossover, interweave. So this is called woven fabric, okay, interweaved. The second one is more like the pie fabric. It's more like this carpet. Underneath, there's a piece of fabric, and some fibers stick out. Okay, and then there are two modes of deformation. One is if you apply the electric field, sorry, not the electric field, the magnetic field, and along the directions, I need to show here. You see, it's not in XY direction. Then the fabric will bend. Okay, this is bending, and then you put on the pipe route, and there are two ways. One is you apply in this direction, and the individual fiber will bend, or they stiff, become like this. So like a brush, or like you can touch your dog. You feel all the hair go softly underneath your palm. The other one, unfortunately, all stick together. Okay, stick together, and this hair become stiffen. Stiffen, its bending rigidity actually increased by 30 times. From very soft one become very hard, like this. Okay, you can think how can you apply this to many applications. Now, this is a recent work published in Nature end of last year, I think. So I explained that this is actuating, top one is woven fabrics. You have two group of yarn, one is black and one white, and you intertwine them together, making the fabric normally people wear as outerwear, not a t-shirt. T-shirt is another structure. Okay, this is a woven structure. You have this distinguished two way. One is bending, the other one is stiffening. And then with the brush, this pile of fabric, and you can bend, or you can let them straight. Okay, the thickness actually change. And if you have such a fabric, we have a demonstrating piece in the lab. Somebody put fingers on them, feel, oh, it's very smooth, because fiber is very fine. It's a 20 micron, less 1/4 of your hair, so you can feel very smooth and nice. And certainly when you apply the field, it becomes like a brush. Okay, so the way we communicate the so-called handle, I explained to you, I feel this is a stiff, I feel this is a smooth. You can quantify it, reproduced miles away. Okay, and yeah, this is a little bit technical. Probably I'll give it a skip. So this fiber, this is a little container, actually contain 4 kilometers, because it's a very fine fiber we made. And they making to the assembly, and they connect it. And nicely, this fiber actually is not uniformly magnified. And it has a structure and isotropy, as shown on the bottom line in the middle one. in the axial direction and in the vertical direction, actually they are different. So this can be used for design special for certain purpose. As a mechanical engineer, people will think how you can utilize this kind of a behavior to make functions. Now, talk about bending, probably most people wouldn't know. Thin rods under magnetic field, they were bent. And yarn that's made of many fiber twist together and behave similar. So the top square is a similar behavior. But unique thing about is stiffening. If you have a yarn, put them on as a beam, supported at both ends, and then you apply the field along its axial direction, and then you put a force there. The force actually increased from the black to the pink many times. Okay, so at a certain strength of the magnetic field. Okay, so displacement. This is you can see at 250 or 280 millitesla. M Tesla, this is a safety limit for human. Okay, so we do not do anything beyond that because safety issue. So we put this. So when the field increase, the reactive force increase, and probably people will know the hysteresis is this area under the same color increased. This is something unique about this fiber assembly. It's because of friction between fiber. And when you apply the field in this direction, the fiber tend to sort of crawl together, contract together. So squeeze other fiber, increase the friction. So that area is bigger. Okay. And these certainly reflect combination of the change of geometry and the friction contributed to this last diagram. You can see field changed from 0 to 280, and bending rigidity increased quite a lot, right? Maximum one of the optimized ones nearly 30 times. What is the best one? People will say it's 100. But that is shape memory alloy. Shape memory alloy need a lot of energy and a long time and heated at a high temperature. But this one is room temperature, friction of time, in simultaneous deformation. So for quite a lot of applications, this is certainly is more advantage. And of course, this fiber and this fiber structure can be further improved to increase this type. Okay, so it's like a locker. You can certainly switch on and off. So if somebody said, what about it? This person is walking and suddenly he nearly fall off. Then the pants stop him to fall. That certainly is possible because the dynamic response of this structure is very fast compared with other technology, other materials. Okay. So I show a video of how under the field the yarn will behave. You can see this yarn fiber. Initially, sorry, this is already towards the end. Let's start again. Initially, the fiber evenly distributed, then become grouped together. You can see that is a contraction. They squeeze other fiber together. So that is the reason why we have a large hysteresis and a large increase in bending rigidity. Okay, so once we have that, we make them into fabric. On the left side, you can see this woven fabric, and the second row on the left side, that's a pipe fabric. So you can touch them, And apply field and the pipe fiber can go one side or can go stiffen in other direction. Of course, it can go to other side. So it's like 中文就墙头草，墙头草，往这边，往那边。然后you can think about design. It's exciting. It's you wanna have a tapestry, and then you see that tapestry. Certain part is going one way, the other part go to another way. You have a lot of artist work that way. Okay, so quite a few people talking to us to trying to utilize to make it. Another one is a piece of fabric on the right top side, and you put on that fabric. You cannot hold. You stretch it. You let it go. It fall down, right? And in this case, they're put into a field, and then it is stretched up, straight in the middle. A weight is dropped on them. It doesn't fall. Once the field is off, the whole thing fall down. So it's like the flying carpets in Middle East tale, right? Fairy tale, they're flying carpets. Somebody can sitting on them fly. It's exactly what happened here. Okay, you cannot see why the fabric become one piece suspended in the field, in the air, because the field is applied to it. Okay. Now, here we have a 3 demonstration of devices. The first one is a linear actuator. Linear actuator is showing the first row, left 2 side. And you can see the heights go up from initial initial very short and become very large, right? There's a 5 millimeter in displacement. And the mechanism to do this is you can put it into a ventilation device, like showing the C. Initially, they squeeze together, and in the middle, when the height going up linearly in this direction, and it opens up some ventilation opening in fabric. So when the weather is hot, it can let more hot air out. When it's closed or when it's cold, it's shut down. Okay, and also in filtration, if you want to filter large particle, you can open up. If you want a small particle, you can close down. So in industrial application, linear actuation, we can use this one. And second one, I don't know whether it's interesting or not, is a soft grip. This pie fabric, 2-piece fabric, grow a worm, a big worm, from bamboo worm they call. That's the first one, it's alive. The second one is a tofu, soybean curd, white one. And this fabric, grab it, look at the surface, a little bit careful. There's no mark on the tofu because the force is carefully controlled. The third one is a bean cake, 绿豆糕. That is a lot of granule in there and can grab it without fall down all the particles. And then blueberry. Blueberry, I think, is easier. But the shape is a little bit blueberry, yeah. Then the next one, even weird. We have chips, potato chips, I think. That is very easy to break. And, but this grip is pretty good. It's a big toy for students. This is Italian noodles. Not really noodles, have an Italian name. Yeah, that shape is very irregular, so it says can grip irregular. Okay, I think that one probably says as a crepe fabric is pretty good. Then I talk about the communication of handle. These glove finger actually can communicate the feeling of finger touch. For instance, if you twist your finger, you hand it on them, you feel there's a force there, or you have something move, you feel the movement there. So this finger can duplicate this kind of movement and force remotely on a second user. Okay, and this is how to control them. You control basically the frequency and also the amplitude of the current getting to those Y coil. Okay, that's control the field. And that's the first one. Second one, you control the feeling of roughness by also control this. And you touch one person where this finger glove touch a surface that registers all the signal and then duplicate somewhere else on another person. That person feels the same because the signal is the same, response is the same. Okay. And of course, this one will be used for education of designer, because in design, the people look at the color. We have image and shape also. But when people talk about handle, sorry, cannot communicate. How can I say this feel silky smooth, the other one feel rough? Okay, this in the classroom, we can have students wear this glove, and the teacher give an example, and then everybody know how this feeling can be somehow unified. Otherwise, you talk about your feeling, I talk about my feeling. We cannot communicate, right? No agreement. So this is something will be further developed. Okay, I have said the first three. Now go to the last one. Last one is, it's a little bit weird. It's a fabric inside has a lot of fluids. And the reason probably people can think about robotics have one kind of driving mechanism put a fluids in there. And the other one is for cooling or for heating, like a water bed. I don't know whether you ever use water bed. It's nice. Nowadays, not for long ago, probably a month ago, I saw news in US, somebody got a $40 million venture capitalist funding to fund a waterbed, heated, sectionally heated or cooled waterbed, okay, and for sleep, okay. So our motivation for this is for recovery. Sportsmen between exercise or between competition, they need a very fast recovery. How can you do this? Nowadays, one practice is they have 2 buckets of water. One is icy water. The other one is hot water. Icy water 5 degrees, hot water 40 degrees. So the person jumps in the sequence, I have to think, first into the icy water, and for 1 minute, and jump to hot water for 1 minute, and back and forwards 5 times. That's the current practice. If we go to a sports institute, you will see they have all these buckets of this big one. So one person have one pair, and it's impossible to do that in competition field. In training, probably you can do that. And also, it's not really very good. Use such a large quantity of water to cool body down and up. So our motivation of this work actually is practically driven. They want a wearable device, replace that water bucket. So the challenge is, when you put it on human beings, you cannot have arbitrary boundary, right? You must cut it into certain pattern, we call pattern. It's unlike the tree or the tidal. They have a very nice path, efficient water pass or network to get the largest area in shortest time. And, but in our case, we have a fixed boundary. The engineer problem is you have a fixed irregular boundary and a fixed inlet and outlet of the fluid. How can you achieve large area, even spread of fluid in a short period of time, and then have a most efficient heat transfer? That was the question. So to do this, how we do that? We have a multi-layer fabric. Multi-layer fabric, top layer and laminated with a waterproof membrane, and bottom same waterproof membrane. It's like a bag. But a bag, if without any constraint in the middle, they will expand, right? Like a balloon. You cannot do that. So there are connections like these pen van, or we call wall network. Yeah, I'm pretty sorry. It's like this is a piece of paper, or this pattern on your leg, the whole leg, okay? And this part, these two fabrics are connected in the middle, adhered by heat adhesion. And then there are a lot of dots in there. The purpose of that to allow the water flow very fast, equivalent to this person jumped from one bucket to another in between 10 seconds. That's a requirement. And the energy transfer here, we're talking about probably in terms of power is a kilowatts. Very fast, a very large amount of energy transfer. Okay, so how can we design such a structure and achieve those goals? That was the study, the purpose. And use least amount of water, least amount of heating or cooling energy. So how is my time? Oh, yeah, I think I will be very fast on this one. So all the mathematics are a little bit boring. But anyhow, we did the modeling, and then we have developed a certain methodology called topological fluid network design to find the optimum solution. And because this piece of fabric is unlike a normal heat transfer panel, they are fixed and rigid. This is flexible, they change. When you put more water, they become thicker, right? And less water, they become thinner. The shape and contact will change. So there are a bit of adjustment and corrections to do. And to do experiments to verify it, and in the end, do it on human legs. You can see this. Achieve certain goals I mentioned earlier. This is the infrared picture. Initial one, 0 seconds. You do not take any temperature, room temperature and the panel temperature is the same. When you put a cold water in there, 10 seconds, reach 3.6 degree. And then very even, large area, very quickly filling this large period. It's quite a big, large area. It's about a half square meter big panel, okay. And next one, at a 60 seconds, certainly you put a hot water in there. The hot water in 10 seconds also evenly distributed. Okay, 40 degree, nearly 40 degree, and keep there. And so it does this cycling, okay. And this work actually benchmark against the current technology. In cold cycle, in hot cycle, they both are close to water immersing. That's the jump into water, very close. You can see it here and here. And the others reported work and a commercial one, all on the bottom. So that achieved a very good results. And as a result, this is made into not really commercial, it's a prototype for the wearable device. used by our sportsmen in Hong Kong Sports Institute for training. Okay, and I think I have run my time out, and I better to acknowledge all the funding body and all my students and the group. And thank you very much to share with me our some thoughts. And please, if you have any question, please ask. Thank you.